The universe is a vast, uncharted ocean, stretching out in every direction far beyond the reaches of our imagination. Even the closest stars are separated from us by distances so immense that they boggle the mind. For centuries, humanity has gazed up at the night sky, dreaming of what lies beyond. Distant worlds, other galaxies, perhaps even other forms of life. Yet, as our understanding of physics has grown, so too has the realization that these dreams are held back by a relentless obstacle: the sheer scale of the universe. Traveling from one star to another, or even from one side of a galaxy to the other, would take thousands or even millions of years with our current technology. Is the universe simply too big for us to ever truly explore? Or could there be a hidden shortcut, a secret doorway through space and time? This is where the tantalizing concept of wormholes comes into play. Wormholes, sometimes called Einstein-Rosen bridges, are one of the most fascinating ideas ever to emerge from the world of theoretical physics. But what exactly are they? To decode this problem, watch until the end. A surprise awaits you. Subscribe to the channel now so you don't miss out on valuable knowledge, and join me on the journey of independent scientists. Imagine for a moment that the universe is like a vast, flexible sheet, a fabric that can be bent and twisted by massive objects. Normally, to get from one point on this sheet to another, you'd have to travel along its surface, covering every inch of the distance in between. But what if you could fold the sheet, bringing two distant points right next to each other? Suddenly, a shortcut appears, a tunnel connecting places that would otherwise be separated by unimaginable distances. This, in essence, is the basic idea behind a wormhole. To decode this problem, watch until the end. A surprise awaits you. Subscribe to the channel now so you don't miss out on valuable knowledge, and join me on the journey of independent scientists. The mathematics that gave birth to wormholes come from the mind of Albert Einstein, who revolutionized our understanding of space and time with his theory of general relativity. In 1935, Einstein and physicist Nathan Rosen discovered that the equations of relativity allowed for the existence of these hypothetical tunnels through space-time. In technical terms, wormholes are solutions to Einstein's equations that connect distant regions of the universe. But while they are mathematically possible, their actual existence remains one of the great unanswered questions of modern science. Not all wormholes are created equal, and over the decades, scientists have proposed a wide variety of types, each with its own unique properties. Some, like the Schwarzschild wormhole, are simple in theory, but deeply problematic in practice. These non-rotating wormholes quickly collapse into a singularity, a point of infinite density, making them impossible to traverse. Others, like the Reissner-Nordstrom wormhole, introduce electric charge into the equation, while Kerr wormholes add rotation. Each new factor adds layers of complexity, and each comes with its own set of challenges. But what really captures the imagination is the idea of a traversable wormhole, a stable tunnel that could, in theory, allow people or spacecraft to pass safely from one mouth to the other. These traversable wormholes, also known as Lorentzian wormholes, are the kind that populate science fiction stories and fuel our wildest dreams of interstellar travel. Yet, even in theory, keeping such a wormhole open isn't easy. The universe, as we know it, is hostile to these shortcuts. Gravity wants to pull everything together, and a normal wormhole would collapse in on itself before anything could get through. This is where the concept of exotic matter comes into play. Unlike ordinary matter, which has positive mass and attracts everything else with gravity, exotic matter is a hypothetical substance with negative mass or energy. Instead of pulling things together, it would push them apart, creating a kind of repulsive force. If exotic matter exists, it could, in theory, be used to prop open the throat of a wormhole, counteracting the crushing force of gravity and allowing the tunnel to remain stable. It's like using a strange, invisible scaffolding to keep the walls of a tunnel from caving in. But there's a problem. As of now, exotic matter remains purely hypothetical. No one has ever observed it in the laboratory or in nature, and creating it would likely require energies far beyond anything we can currently achieve. The very idea pushes the boundaries of what we understand about the physical world. Until we can find or create this extraordinary substance, traversable wormholes remain a dream, a tantalizing possibility, but one that is forever out of reach. Suppose, for a moment, that we did find a way to stabilize a wormhole, perhaps by mastering exotic matter or discovering some new law of physics. What would it actually be like to travel through one? Imagine a spaceship approaching the mouth of a wormhole, a shimmering, swirling gateway suspended in the void. As the ship enters the throat of the tunnel, the very fabric of space would warp and twist around it. In the blink of an eye, the ship could emerge from the other side, light years away from where it started. The possibilities for exploration, new worlds, new civilizations, even new galaxies, would be endless. But this journey would not be without peril. The forces at play inside a wormhole would be unimaginably strong. Tidal forces, differences in gravity from one end of the ship to the other, could stretch and compress anything passing through, potentially tearing it apart. High-energy radiation could flood the tunnel, posing yet another deadly threat. Even if we could build a wormhole, making it safe enough for human travel would be an enormous challenge. As if that weren't enough, wormholes open the door to an even stranger possibility: time travel. According to Einstein's theory of relativity, if one mouth of a wormhole were accelerated to near light speed and then brought back, time would pass differently for each mouth. In theory, this could create a time difference between the two ends of the wormhole. Someone entering one mouth could exit the other mouth at an earlier point in time. This raises all sorts of paradoxes and puzzles. What happens if you go back and change history? The famous grandfather paradox asks, if you traveled back in time and prevented your own grandfather from meeting your grandmother, would you ever have been born? Wormholes, if they exist, challenge our very understanding of cause and effect. Despite all these mysteries and challenges, wormholes remain one of the most exciting frontiers in theoretical physics. They force us to confront the limits of our knowledge, to ask bold questions, and to imagine futures that are both thrilling and strange. Will we ever find real wormholes out there among the stars? Could we one day harness their power to explore the universe, or even travel through time? Or will the secrets of wormholes remain forever out of reach, tantalizing us from the edge of possibility? If you've watched this far, congratulations! You are truly a passionate scientific explorer, always persisting and conquering every challenge. Let's subscribe to the channel so we can keep on discovering together. For now, the answers remain hidden in the cosmos, waiting for the next generation of scientists, dreamers, and explorers to uncover them. What do you think? Is faster-than-light travel through wormholes just a fantasy? Or could it one day become reality? Where should science look next in the search for the universe's greatest shortcuts? The universe is full of mysteries, and the adventure of discovery has only just begun.